food for thought for your future workflow. We've dedicated an hour to this, which includes a Q&A session at the end. However, please feel free at any time if you have a question to either use the hand icon at the bottom of your screen, which will alert us that you would like to ask a question, or alternatively, please type in the chat icon and I can ask the question for you. So Patrick King, our Senior Field Application Specialist in the UK, will be giving the presentation today. He has been with RedShiftBio now for 2.5 years, but prior to that, he studied chemistry at Bristol Uni, where he went on to complete a PhD in protein biophysics. Later, he did a postdoc in Manchester for 5 years, which then led to 2 years with Malvern Instruments, covering a range of techniques. Over to you, Patrick.
Thanks very much, Natalie. Hi, everyone. Thank you very much for taking the time to listen to our presentation. I'm going to start the presentation just with an overview of the company, RedShiftBio. Then I'm going to go through some of the technology itself and how it works. Give you a couple of examples showing the kind of information you will get from the system, and then take you through some application examples to give you some ideas of how you might use the system to help you with your research. So this is a picture of the system. It's called the AQS3pro, and it uses a technology called Microfluidic Modulation Spectroscopy. The system itself has quite a small footprint. It comes in 2 halves, the smaller unit containing the computer and some pumps, the coolant, which is non-liquid nitrogen based, and then the larger unit in the center of the screen is where the laser is housed, the flow cell is housed, and where you would load your samples in 24 or 96 well plates to collect the infrared information the system generates. So who are RedShiftBio? We're a relatively new company based near Boston in Massachusetts in the US. We're quite a small startup company, but we are backed by 2 of the largest instrument manufacturers in the world, one of whom we can't disclose, and the other of whom is Waters. We are the inventors of microfluidic modulation spectroscopy, and we have produced a system that contains this technology called the AQS3pro. We've designed the system from the ground up, alongside the software by which you run the system itself, called AQS3 Delta, and this also houses a very powerful analytics program as well. We launched in 2019, shortly before, unfortunately, the COVID pandemic has struck the world. But as you can see, we have quite a large worldwide presence. We have companies we have systems sold to the companies shown on the screen here, largely in America, but also in Europe, and we're actually spreading out around the globe, despite the pandemic hitting us right at the wrong time, of course. We also have, in Europe, we have European applications, local support, and we also have local service support as well. So this is a protein analysis tool. And if we look at proteins, there are perhaps 5 main attributes that people are most interested in measuring for their protein samples. These would be quantitation, so quantifying the amount of protein in the sample, getting an idea of the structure, or particularly the secondary structures present within the protein sample itself, using this as an absolute characterization tool, but also for use in similarity analysis, perhaps comparing, using it as a QC tool for comparing batch to batch, or perhaps looking at different formulations. Also maybe looking at its stability, its shelf life stability, or its stability to different excipients or conditions that the protein is stored in. And also some information as to the aggregation state of the proteins, which is very important, particularly in therapeutic products. Now, there are systems in place for each one of these measurements already, as the pictures indicate. But the point is here that there is no one technique that covers all of these measurements in one measurement. And each one of these different techniques suffers from some sort of limitation, whether that be the dynamic range, both in concentration and in the background conditions that can be measured. Perhaps there is complicated methodology or low throughput, or perhaps there's no fully automated system in place. The AQS3pro makes all 5 of these measurements with each sample you analyze. And this is where the name comes from, in fact. So A, Q, and the 3 S's make up the AQS3pro. And we have brought a system to market that doesn't suffer from the limitations of the technologies that I just showed you on the screen. We have an extremely wide dynamic range, being able to do structural analysis on your protein samples from 0.1 to above 200 milligrams per mil for structural analysis, that is, and also an order of magnitude lower for quantitation, so measurement of the concentration of the protein in your sample. We also have exceptional spectral reproducibility. We have measured above 98% spectral reproducibility for a lysozyme sample that we use as a standard at 2 milligrams per mil and above. And this really increases quite dramatically the higher in concentration you go. For example, for a 100 milligram per mil MAB sample, I've personally recorded a similarity of 99.93% between replicates. These measurements are made automatically from well plates, either 24 or 96 well plates. And the measurements can be made irrespective of the background conditions, very importantly, which allows you to directly compare samples across a large workflow. So if we look at the different hierarchies of protein structure, there are 4 of these. And for each of these, there is already an automated process in place or system in place that can make these measurements quite routinely, apart from for secondary structure. For secondary structure, there are 2 major technologies that dominate. There is circular dichroism spectroscopy, which I've used personally quite a lot. And there's also FTIR, Fourier transform infrared spectroscopy. Circular dichroism is a very good accessible technique. In this technique, we're using low wavelengths of light, UV light, and you have circularly polarized light, which is either left or right-handed. And we're looking at the differential absorption of those 2 types of light by your sample. So particularly if you have helical components within your sample, like alpha helices, this technique is very good at making those measurements, but it isn't so good at making measurements of other types of structures, such as beta sheet. There are some reasons for this, but most importantly, the signals that correlate to alpha helix and also random coil are quite well separated in the spectrum. For beta sheet, this is not quite the case. First of all, the magnitudes of particularly parallel and anti-parallel beta sheet are opposite, and they overlay in a very similar position in the spectrum. And therefore, it's very difficult to deconvolute that data and make these measurements accurately. As I mentioned, the circular dichroism technique uses light in the low wavelengths of light in the UV region. So the wavelengths of light are in the hundreds of nanometers range, which is approaching the size of the objects in solution which you're trying to measure. And of course, if you approach the size of the wavelength of light in your solution, you progressively get more and more scattering effects from your solutions. And this means that the circular dichroism suffers from a relatively narrow dynamic range in terms of concentration, with an upper limit generally accepted to be around 5 milligrams per mil. And this also has effects on the types of background conditions you can measure, reproducible to get good data from samples. For example, if you have some common excipients in the background, or particularly surfactants or objects like that, these are getting quite large. Also, the aggregates of the protein samples themselves. These can approach the wavelengths of light that we're using to make these measurements, and therefore we get progressively more scattering from these samples. This has 2 effects. One, it limits the dynamic range that you can actually access with the system, but also it attenuates your signal progressively more towards lower wavelengths, and therefore skews your data and makes deconvolution of the spectra into useful structural information even more difficult. So perhaps a superior technology in this space is Fourier transform infrared spectroscopy. Infrared spectroscopy has a number of advantages over CD. For example, the signals in transmission IR or infrared are all in the same magnitude, so in the same direction. They're also quite well spaced, particularly in a region of the spectrum called the amide-1 band, which contains all the necessary information for protein secondary structures. The wavelengths of light that we're using in infrared spectroscopy are much longer than in CD, or circular dichroism. And so the scattering effects I mentioned previously are much reduced, even to the point of being relatively irrelevant for the majority of samples, meaning that we can access a much higher concentration range for the measurements, and we can measure in a much wider range of background conditions. Now, unfortunately, with Fourier transform infrared spectroscopy, there are a number of limitations to the existing traditional technologies. These are mostly due to signal to noise, which means that we need to generally have quite high concentrations to make accurate and reproducible measurements using standard benchtop systems of this type. And this has really limited its use in biotherapeutics, because what is really required is a system that can access the range of concentrations and also the background conditions that scientists are most interested in for their samples, to give you this useful information, but in a more kind of appropriate regime. Infrared spectroscopy itself is extremely useful. It's a label-free technique. We're using the absorption of the peptide backbone, or the carbonyls within the peptide backbone. So we don't need to have any extrinsic labels on your proteins to make these measurements. We can do quantitation measurements just like you would with UV spectroscopy using the Beer-Lambert law, but using the peptide backbone or the protein backbone as the chromophore. But we can also get some really good information on the secondary structure state in that your proteins are adopting in your sample by looking at the changes in frequencies that these carbonyls absorb at, depending on their hydrogen bonding network. The hydrogen bonding network they're involved in, which relates to the type of secondary structure they're involved in. And because we have such a wide dynamic range with MMS and the AQS3pro, this means that rather than being limited to a kind of narrow range of this biotherapeutic pipeline, we now have a technique that can equally easily make measurements at low concentration and perhaps simple buffers like PBS in the discovery phase of the biotherapeutic pipeline, equally easily at that point as we can in a very sticky, complex mixture that the product might be formulated in at much higher concentrations. That's great, and we're not saying that we would replace all of these different technologies here, but the point is that MMS can give you structural insights that go alongside all of the other established techniques within your biophysical toolkit. So why is secondary structure important, and what information can it give you? Well, it can give you a lot of information. There are many applications here, and this is by no means a full list. We're looking at direct signals label-free in your samples, and we're looking at the changing in structure or secondary structure of your proteins in response to a variety of different factors. Some examples of these might include some structural information to go alongside your ligand binding studies, to have a handle on the protein stability in terms of its aggregation. We can particularly look, as the picture indicates, at the formation of antiparallel beta sheets, which are the most common form of structural aggregate that might form within your sample. We can use the technique for formulation development, for stress testing, for a biosimilarity approach. We can use it for QC in batch-to-batch reproducibility. And because of the sensitivity of the system and the reproducibility of the measurements, which are extremely high, we can also use this technique in accelerated stability studies as well. So amongst those benefits, we also have a system here that is that reduces the measurement time for compared to FTIR by about 20-fold. And we have a system that is about 30 times more sensitive than a standard benchtop FTIR type system. And this can be used to de-risk your product failures downstream at a much earlier stage, and to provide you with some key information at a much earlier stage in the product development pipeline in order to make informed decisions at an earlier stage. So how does it work? Well, there are four main features of the system that really separate it from the traditional technologies. The first of these is the light source. We use a quantum cascade laser in the system. This is an extremely bright light source, about 1,000 times brighter than a standard black body illumination source used commonly in spectroscopy with gratings to give you particular wavelengths. In this case, not only do we have a much more powerful laser in the system, but we also have a system that has a much narrower bandwidth of emission, having a bandwidth of emission of about 0.004 nanometers. With infrared spectroscopy, some of the reasons that cause the lack of or the lower sensitivity that I mentioned previously are due to a few factors here. First of all, we need to be able to penetrate the sample itself and the background conditions it's in, and so effectively get light through the sample. One of the major problems in Fourier transform infrared spectroscopy is that in order to make a measurement of your sample, we would normally make a measurement of your sample in its background, or sample in its buffer, and take a spectrum of that. Then we would take a spectrum of the buffer itself and subtract the two to give you a spectrum of your sample. The problem with this is that the measurements are made in usually in a cell that's IR transmissible, such as a calcium fluoride cell. And being able to match these cells is very difficult, particularly if you need to clean these cells, as they're made of quite a fragile material. And so being able to do that very accurately is very difficult and leads to some difference between the measurements you make, and therefore some increased noise. There is also another problem, and that is that water, which is present in most of your samples, absorbs directly in the middle of the region of most interest, which is the amide 1 band. And this, in some cases, might obscure your data and therefore require higher concentrations of sample to make an accurate measurement, but also may skew the baseline when you're doing the subtraction, and has always caused quite a lot of problems with Fourier transform. We get around this problem in both problems actually, but particularly the water problem by using a QCL. It's not only more powerful, but we also can use the narrower emission band to not fire the laser at exactly the position at which water absorbs in the spectrum, but to just go around the edges of it, so minimizing that effect. We use this QCL in combination with a microfluidic flow cell. So instead of the traditional approach of using two matched cells in traditional FTIR spectroscopy, here we actually have one cell with two inlets, and the measurements are made within the same position in that cell. A picture of this cell is shown in the top right of the screen, and I should say this is a cell that is the heart of the machine, but can be swapped out for another that you might have as a consumable piece in the laboratory. So just as with traditional technologies, we'll make a measurement of our sample in its buffer, then just the buffer or the background itself, and subtract the two to get what's called a differential absorption spectrum. But because we're using a microfluidic flow cell, which has this Y shape, as you can see in the diagram and towards the bottom left of the screen, what we do in MMS, which is where the name Microfluidic Modulation Spectroscopy comes from, is to first load the cell with buffer and to make a measurement of that at one particular wave number. We then hold the two fluids at pressure behind two valves, and we rapidly modulate between the two in order to make these measurements very accurately and we make several repeats of each measurement at each wave number, subtracting out any differences between the two channels in real time, which first of all accounts for any subtractions of the buffer, but also subtractions of any water signals that might be present in the sample. We also control the humidity of the chamber in which the measurements are made as well, further reducing the effect of that water peak. And we also, because we're doing this at quite high speeds, between 1 and 5 times a second, we also account for any variations that are present with every light source that you might use in spectroscopy. And the final benefit here is because we're using such a high-powered laser to make these measurements, normally for a transform infrared spectroscopy, you would need to use a liquid nitrogen-cooled detector. We have such a higher output from our laser compared to these traditional light sources that we don't need to do that. And we actually just use an internally cooled system using a polyethylene glycol based cooling fluid. And so despite the fact that we're not using this cooled detector, we actually still get this 30 times increased sensitivity compared to traditional systems. Oh, excuse me. When we're making these measurements, we're making measurements every 4 centimeters to the -1 across the spectrum. We're making repeat measurements at each data point, and then we're interpolating that spectrum to provide you a spectra by which we do further analysis. In addition to this, as I mentioned at the start of the presentation, the system is fully automated, and we run samples from either 24 or 96 well plates. This means that rather than the traditional approach with Fourier transform infrared spectroscopy that generally needs quite an expert user to make the subtractions correctly between the two channels and to give you good, reproducible, robust data, we don't need to do that. We instead will set up a method in the software via a drag and drop interface. The system can run samples in any order from the well plates, and it simply takes the samples and references loaded in pairs on that well plate and sequentially loads them into the system and runs them in an automated fashion with error handling options that keep the system running in case of any aggregates or other issues with the samples there may be. We would generally run the system actually overnight, particularly from a 96 well plate. And so we have a well plate chiller in place in case you have any concerns as to your samples decomposing over that timescale. And I should also say the system is also fully automated in terms of checking the health of the laser, for example, on startup. And you can also build your methods so that the system will check cleanliness of your cell and also put cleaning steps in between the different steps within your protocol in order to make this a fully automated procedure. And finally, we have a very powerful inbuilt analytics program that again was built from the ground up by the team at RedShiftBio. So what do we do with your data? Well, I've covered this so far. This is the differential absorption spectrum we'll record for your sample. This is the direct or the raw data we collect, and we interpolate this to provide a spectrum. This appears to be a spectrum with one major peak in it, but actually we do second derivative analysis, or taking the gradient of this line in order to pull out the spectral features that correspond to the different secondary structures present within your sample. We invert this and baseline it, and then do a Gaussian curve fitting analysis to deconvolute this information into useful secondary structure information that we output in percentage form, which is fully user selectable depending on the model that you may use from the literature, which is also fully user customizable. And I should say that you can see every step of this fitting procedure in detail at every stage. So this is the kind of workflow that we would normally generate, or the types of information that the system would generate from every sample, or particularly in this case from a plate full of samples. Here we have an example of a MAB fragment that's been incubated at a variety of temperatures to look at the structural changes that accompany it. So we start with the raw differential spectrum. We calculate the concentration as part of the measurements in comparison to an internal or a customer selected reference that can be very simply measured just by taking a measurement on the system. The system then will generate these outputs. The workflow I showed you just now is the one down the bottom, where we would do the Gaussian peak fitting analysis to provide higher order structure data in a bar chart format. But we can also look at this data in a variety of other ways. We can look at the raw spectral signals themselves, particularly in the second derivatives. And we can do a delta plot analysis of this, or a difference plot of the second derivative, in order to look at changes between, for example, a reference sample and the others, to look at where the structural features are changing over time. And we can plot this further on what we call a stability plot, customizing this plot as the user requires, following, in this case, signals for anti-parallel bead sheet, which is this one here, and parallel bead sheet, which is this one here. So therefore, looking at the decomposition of the native structure with increasing temperature in this case, and the formation of anti-parallel bead sheet, or a structural amyloid type aggregate as the temperature increases. All plots shown on this slide are actually directly from the software itself. You can copy the data points out by just right-clicking and copy paste into Excel, and you can copy any of these diagrams as well simply by pressing copy and pasting into excuse me, something like a program like PowerPoint. Sorry, and one last thing, we also generate PDF reports that you can again customize as you need to for these runs. We have a couple of other ways of looking at your data as well, in addition to what I've just showed you. These are two types of mathematical analyses to look at changes in your sample. And this can be very useful if you don't know exactly what fitting model to apply, or you don't want to go down the more derived data that is generated in that way. We can look at the direct spectra themselves and simply compare them mathematically to one another, perhaps to a reference sample that you've added as part of your run. We can do this mathematical analysis by area of overlap. So looking at the whole spectrum, or we can actually look at, we have a variety of options. We can look at certain parts of the spectrum and so on. And we can also do this by weighted spectral difference as well. And finally, the software is actually very user-friendly and open. A lot of the files that the system generates are very small, and they're text files, so you can look into the details to any level you would require. But if you would like to, as an optional extra, we do also have 21 Part 11 compliant ready software that you can use to prove that you are compliant in 21 CFR with our system. And this will give you things like different user account levels and so on, and you can customize this as you require. So I hope that's a good overview of the system for you. I just wanted to show you an example of the data generated by the system. In this case, for a NIST MAB, this is a standard sample purchased commercially, and one that is known not to vary structurally with concentration. And as you can see, this was all run on one plate easily within a single day. And we did a concentration series from 2 milligrams per mil to 70 milligrams per mil. The absorption, the raw differential absorption spectra that I first covered are shown in the top left. The second derivative in the top right, and this is the higher order structure output of this sample set. And as you can see, this confirms that we're not seeing any structural differences at the different concentrations. This is a quantitation plot that's generated by the system on the left-hand side. And I'm just showing you this because this is a really good measure of how reproducible our data or our spectral reproducibility across this concentration range is. As you can see, we've fit this data to a straight line fit, and the R squared of this fit is 0.99998. which is extremely high and is reflective of the very, very high reproducibility of the data generated by the system. Excuse me. And then just to compare it, in addition, we've got a table of results that is also generated by the software with every run. Here, looking at the reference sample using the 2 milligram per mil sample as the reference, and comparing the overall similarity of each spectra to that reference by area of overlap analysis. And finally, we have also measured the concentrations of each sample very precisely using a similar method to the Beer-Lambert law, but again, using the backbone as the chromophore in this case. And you can see they're very, very close to the nominal concentrations given to the system, but not quite. So I'm going to take you through a number of different application examples now. The first of these is a study, a really interesting study performed by Elian Labs in the US. And in this study, they wanted to understand what the sensitivity limit of our system was, and particularly in comparison to the other techniques in this space, circular diprism spectroscopy and Fourier transform infrared spectroscopy. So to do this, they used a model system. They used a combination of IgG, which is predominantly beta structured, and BSA, which is predominantly alpha helically structured. And they simply doped precisely known amounts of one into the other to determine at what limit, what the quantitation limit was, at which we could determine the presence of one of these materials in the other. So in this study, they produced a paper that covered this work, and they quoted the values of this limit in terms of the limit of quantitation. So like I said, we compared a benchtop FTIR system, an MMS system, and a circular diprism system. Looking at the limits of quantitation measured with the different techniques, you can see with FTIR, at 20 milligrams per mil, we have a limit of quantitation of 23%. That means that we would need to see a 23% difference in structure between two samples, for example, in a stress test or a formulation series or something like that, in order to know that we have a reproducibly different structure within that sample, which is really quite high. For CD, this is much higher, much lower, sorry, at about 3.7%. But we are constrained to the concentration limit of about 1 or 5 milligrams per mil. But with MMS, this beats both techniques. The limit of quantitation with this technology is 0.76%, which is very, very high. And that means, just to clarify again, we can make measurements of differences, measurements of differences of secondary structure of less than 1% within your samples. This makes it about 30 times more sensitive than a standard FTIR type system, and about 5 times more sensitive than a CD system. And in addition to this, we have a labor time saving, quite a significant labor time saving, by introducing the automation to this system as well. To run these samples in FTIR, I estimate it would take about 5 hours. For CD, maybe it's a little bit less, at about 3 hours. For MMS, the direct user time required to run to prepare the samples and run the system, generally, as I said, overnight, is about 30 to 40 minutes, depending on the complexity of the run, of course. Okay, so I just want to show you another example here. This is of an ADC, and this is looking at the structural effects of the conjugation of a MAB to form the ADC. So in the top, we have just the higher order structure breakdown of the MAB itself. And you can see it's predominantly beta structured with also a lot of turn structure in there. The group did the conjugation and then wanted to understand whether or not the structure had been affected by this conjugation. And in this case, as you can see, there was absolutely no change in structure. So this confirms that this conjugation does not affect the ability of the MAB to form its native structure. We can also look at perhaps an ADC under stress conditions. In this case, we have an ADC under pH stress, where it's been held at pH 3 for 3 days. And in this case, we can see there is quite a large difference. The data here is shown in replicates. So there are 2 replicates of each sample. The control is shown on the left-hand side for each different type of secondary structure, and the stress sample on the right-hand side. So you can see that the native structure has fallen off. We've lost some of the parallel bead sheet that we measured at the beginning of the study. And conversely, we've seen an increase in the amount of anti-parallel bead sheet, which is often the cause of a structural aggregate within your sample. In a second sample, however, we don't see this effect. So with the same conditions, this ADC number 2 is pH resistant, and in this case, we don't see any changes in structure. Now, all biophysics all biophysical techniques are useful, of course, but by using them as a toolkit, you provide the most, or you gather the most information for your samples. So this is an example of using MMS in combination with one of those, in this case SEC, or size exclusion chromatography. In this sample, we've stressed the sample at 50 degrees for 10 days. And as you can see from the MMS, there is absolutely no change in the native structure under these conditions. However, with SEC, we do see the formation of not just a monomer peak here, but also some sort of aggregate peak here, and perhaps 2 of them, but with no change in structure. When we increased that temperature to 70 degrees for a shorter time period, we actually saw now some changes in the structure. We saw, again, a fall off of the native parallel bead sheet structure and the formation of an anti-parallel structure within the sample. And if we look at the SEC, we actually see now the same monomer peak, but much smaller actually in this case, and the formation of a large number of aggregates. In this case, perhaps 2 peaks or a shoulder on the first peak here. And so in combination, this information shows you that we have perhaps 2 types of aggregates forming within your sample. Perhaps maybe this might be a colloidal type aggregate on the left-hand side, where we don't have any changes in the native structure, but perhaps the natively structured proteins are adhering together. And on the right-hand side, by using MMS to give you the structural information, we now understand that there is a 2-stage process. And in this case, we're perhaps unfolding that protein and allowing it to form these amyloid type or anti-parallel bead sheet structures, or a structural aggregate. Aggregates are extremely important to our customers, and very important when looking at a protein therapeutic in general. And so we did another study here with a group called or a company called Pressure Biosciences in the US. This is a really interesting study because Pressure Biosciences have expertise in the formation of aggregates as control samples. In order to prepare some control aggregates for this study, what they did is they took IgG and they subjected it to extremely high pressures, 55 kilopascals, in order to fully denature or to fully change the structures of those samples to an aggregated form. We could take this sample and combine it with a native unstressed or untreated sample, and therefore know a little bit like the alien study I showed you earlier, precisely how much of the aggregated material we had doped into our sample. We then studied this in MMS. We did this, over with 10 additions of different concentrations of aggregate. And you get some really beautiful data out of the MMS spectra. You can see here, as we're increasing the amount of aggregate, the native structure is effectively falling off because we're making an average measurement of all the structures present within a sample with the spectroscopy. And at the same time, the amount of anti-parallel bead sheet structured material or aggregated material is increasing. We can follow this again by area of overlap similarity or WSD, weighted spectral difference. But we could also do a difference plot of the second derivative data, as I showed you in the workflow earlier. And here we can see, compared to the control sample, we see an increase again in a decrease in the parallel bead sheet structure and an increase in the anti-parallel bead sheet structure as we increase the number of aggregates or the percentage of aggregate in the sample. And we can put this on a line plot, on the stability plot as well, showing you really clearly that as we're losing this native structure, we're increasing the anti-parallel or aggregated structure within that sample. This also allows us to precisely quantitate the amount of aggregate within your sample, again, using this linear line plot with the very high reproducibility of the data. And if you want to look going through the full workflow, looking at the end state of our analysis, you can see pretty clearly here that as we increase the percentage of aggregate within the sample, the amount of parallel bead sheet or native structure is falling off, also some turn as well, and the anti-parallel bead sheet structure is increasing. So a really nice study, I think. We've also done this, of course, on real-world samples, and here's an example of that. This is a protein antigen that has native structure of comprised mostly of alpha helix, shown here, and parallel bead sheet structure. And again, once we subject this to increased temperature, we see the falling off of this native structure and the formation of this characteristic anti-parallel bead sheet structure peak as this molecule starts to fall apart and aggregate. We can use this type of approach in a variety of ways. One of them is to give you a structural insight into some other techniques. For example, your DSC studies, where you might look at changes in the domains that respond to changes in temperature. Here we have another structural view on this process. We can use, of course, all of the outputs of the system, but particularly focusing on the stability plot here to look at the TM of this transition, in this case, in a temperature series, at which we start to see changes in the structure within your sample. We can do this over a really wide concentration range, of course. Here it's shown at 1 milligram per mil for a BSA control sample. Here it's shown at 20 milligrams per mil, and here it's shown at 100 milligrams per mil. And what you see is a progressive increase in this TM as we go up in concentration. This will give you, like I said, complementary information to perhaps your DSC studies or differential scattering calorimetry studies, but also allows you to access higher concentrations than you commonly can access with modern DSC systems as well. We can use this technology in a really wide variety of ways, but I want to give you just two last examples of another two applications that I think are particularly important. One is in QC. Here, this has been previously covered with traditional infrared technologies extensively. This is an example of some published work by Amgen, where they used FTIR to compare some MAB samples with some biosimilars spectrally. This is an example we did with a customer, a European customer. And what we did here is they had a product that required BSA as a reference sample. And despite the fact that they had bought in multiple lots of this BSA from different manufacturers, or perhaps different lots from the same manufacturers, and they came with, say, a HPLC trace and a mass spec to show that they were the same product, actually they found that about half of the products they purchased in worked correctly in their ELISA assay, and half of them did not. And they couldn't understand why. Because the different biophysical techniques they threw at this didn't show any differences between the samples. But perhaps that was down to sensitivity. This is the higher order structure analysis of 14 of these samples, or 13 compared to the reference indicated by the arrow. And you can see they all have extremely similar structures. But as you can also see, there are some small variations that you would probably not see using a less sensitive technology, but we do see very reproducibly with MMS. If we do the second derivative analysis and then look at the difference plot or the delta plots of this, we can see that these samples fall into two groups. I actually use the reference here as the reference sample, so the baseline is the reference sample, and you can see there's a group that falls near this reference sample and another group. You can put this on the stability plot to give you a much clearer output of this. Again, baseline samples are most similar to the reference. Otherwise, they have some structural differences. And it's a very clear way of differentiating between these two groups. The ones closest to the reference in structure work correctly. The ones that are not close to that structure don't work very correctly. But the differences in structure here are about 1% overall, or between 1 and 2%, which is very, very small. You can also do this in another way by just using the simple output of the similarity score. using the reference molecule we were given as the reference to compare the others to. The ones in dark blue shown on this table are the ones with the highest similarity scores, and these are the ones that were functional in this assay. The others were not. And finally, I just want to show you, again, because of the sensitivity and reproducibility of the data generated by the system, an example of an accelerated stability study where we can use these very small changes in structure over shorter time periods in order to predict the effect over much longer time periods. This is another study done in collaboration with a European customer that cannot be named, I'm afraid. But what we did in this study is we took 4 mutants of a control sample that were being studied in-house. And the question was, which one of these 4 mutants was the most stable and which was the least stable due to its mutation under slightly increased thermal conditions. And this was done to simulate the shelf life stability of these products over longer time periods. As you can see, the samples are next to each other, and the samples were either held at 4 degrees centigrade or 30 degrees centigrade for a period of 8 weeks to simulate the stability over years. And you can see there's a pattern here. Between the 2 different samples, we see a slight falling off of, in this case, the alpha helical structure with increased temperature, and indicating that there is some sort of change occurring with increased temperature over time. If you look at these, because these changes are very small, I normalized the changes and compared them to one another in order to pull out the differences on a plot, to really demonstrate that here, in this case, sample 3 shows the smallest changes in alpha helical structure, beta sheet structure, particularly, and is therefore predicted by MMS to be the most stable of these 4 products. Then following up is sample 2, and sample 1 and 4 are about the same as one another in terms of stability. And this was confirmed by the client. We could also do this by similarity analysis as well. Again, the ones that showed the largest difference in similarity between the 4 and the 30 degree sample were the ones that were shown to be least stable. And again, can be used as a different way of predicting this the stability in this accelerated stability study. So thank you very much for your time. I hope you agree that MMS is a real revolution in infrared spectroscopy, simplifying the process of gathering data, speeding the process up remarkably with 96 well plates particularly. We have a system that can make measurements with very, very high spectral reproducibility across an extremely wide dynamic range, both concentration and the presence of difficult components in the backgrounds like surfactants, also organic solvents and a variety of other things. We can make precise measurements of structural change between your samples at below 2% differences. It's a walk-away technology, and we have our 21 CFR Part 11 compliant software as an additional extra. So thank you very much. If you have any questions, please do ask away. Thank you.
Thank you, Patrick. Does anybody have any questions for Patrick at all?
Perhaps I can answer one of my own, or one that I might preempt. How do we know that we're making measurements that are very, very sensitive and reproducible? Well, we make replicate measurements of each sample, or we would recommend that you would make replicate measurements of each sample. And if we want to make measurements or prove that there is a difference between 2 samples, we might make, for example, 3 replicates of 3 replicate measurements of 1 sample that is not stressed. Then we might take 3 replicates of a second sample that is stressed. And what we're most interested in is the internal variance of the measurement of each one of those samples. So for example, if the measurement varies by 1% each time, we can only confidently measure differences that are larger than 1% between the two different samples, and so on. So when we say we can measure 98% reproducible spectra for a 2 milligram per mil sample, perhaps we could confidently measure a 2% difference between two different samples. If we have a sample that is 99.93% reproducible, like the 100 milligram per mil MAB sample I mentioned at the beginning, that means we can make measurements ridiculously small, or measurements of ridiculously small differences between two different samples. In that case, it would be as low as 0.07% differences in secondary structure between those samples. I see a question's just come in. Okay. So do we demonstrate the system? Yes, we absolutely do. We have a variety of options. We can, of course, accommodate some sample analysis for evaluation. We sometimes place systems at different laboratories around the world and bring people to see the system in the laboratory. Or we also do provide on-site demonstrations as well, where we can bring the system into your lab, put it on your bench and run it on your samples so that you can see what kind of information the system will give you for your samples. Are there any buffers that are typically found in protein formulations that are incompatible? Actually, almost nothing. The only thing I've ever found that is tricky is guanidinium hydrochloride at high molar concentrations. So we've made measurements up to about 3 molar, I believe, in guanidinium hydrochloride. But apart from that, I haven't actually found a buffer or background condition that I couldn't measure in. And that's because we have this extremely high-powered laser in combination with the perfect subtraction from the microfluidic flow cell. This means that as long as the background doesn't absorb all of the light that would hopefully pass through the sample and be detected by the detector, we will get a good signal out. At 3 molar guanidinium hydrochloride, that absorbs directly in the middle of the amine-1 band, very, very strongly at that concentration. And so it's probably about 20,000 times the absorption of your sample at that point. And so perhaps that might obscure the sample, but we have made measurements of lysozyme in 2 molar guanidinium hydrochloride and up to 3, where we have only 1/10,000th of the total signal attributable to the protein. And we've still managed to measure reproducible data up to 98% under those conditions, which is truly impressive for a spectroscopic technique, I believe. Okay. If anyone has any other questions, please do feel free to ask, to put your hand up, or to write a message in the chat. Okay.
I think we should wrap it up.
I suppose we are exactly on time. So
yep.
Thank you very much.
That's right. That's great. Thank you.
Thank you, everyone.